So today I'm going to talk about this magic material, right? Graphene, but in a new form. The experiments came earlier this year that showing that it's both conductor, but can be turned into an insulator and a superconductor just under a slight variation of conditions. So this is a very interesting system. So the work I'm presenting here is done collaboration with the people at MIT. Noor and Hiroki are postdocs. Vlad Kozy is my student. Is finishing up, looking for postdoc positions. We also collaborated with Mikito Koshino in Japan. And a lot of discussions with Pablo's group. So we all know that graphene is a two-dimensional sheet of carbon atoms. And in this pristine form, it's actually a very good conductor, despite being one atom thick. So the electrons in graphene move at a very high speed with this Fermi velocity of almost 10 to the 6 meter per second. And it has extremely high mobility, 100 times better than silicon. The carrier density can be changed by a gate voltage. And because the mobility is so high that even at the so-called charge neutrality point, it's still a conductor down to lowest temperature. Now, all the excitement came earlier this year from my colleague Pablo's group at MIT. So what they discovered is that when graphene forms a superlattice, okay, I will describe how this happens in a minute. It turns out there are interesting insulating state of matter showing a lot of physics of coronal electron systems. And further, on a slight variation of conditions, when you go to this insulating state, superconductivity appears, and it's a highly unconventional superconducting state in an all-carbon system. So this is the system that when two layers of graphene are stacked on top of each other, but with a very slight variation, very slight difference in the orientation, so that it's so-called twisted bilayer graphene. The orientation of the two graphene layers are slightly twisted, and then you see that just visually, this is what the structure looks like. It has this long-range, so-called Mori pattern. Some regions, atoms are stacked in one way. If you move maybe 10 nanometers apart, the stacking, local stacking changes. So this basically produces a periodic structure with a much larger unit cell. So this is what I mean by a superlattice. Okay? And at very small twist angles, the superlattice can have more than 10,000 atoms within each unit cell. And the superlattice has lattice constant, which is on the order of, for example, 10 of nanometers for a twist angle of 1 degree. And by contrast, the single sheet of graphene has a lattice constant on the order of 2 angstroms. Okay. So in such a system, again, at charge neutrality point, it remains a conductor, but changing the carrier density by a very small amount, for example, adding on the order of 1 electron per 100,000 atoms, is sufficient to turn this conductor into an insulating state. Okay, that's shown here. The resistivity goes up as you lower the temperature. Okay, this occurs at low temperature. Also, by another slight change of this carrier density, this insulating state gives way to a superconducting state. Right? So we get zero resistance at low temperature. The superconducting transition temperature is about 1 Kelvin, on the order of 1 Kelvin. So all this occurs at ambient pressure, only occurs near the so-called magic twist angle, when the twist angle is about 1 degree, okay, plus minus 0.1 degree. You move twist angle away, then all these phenomena disappear. Okay, so this is a very unusual phenomenon. Just such a small variation of the carrier density turns a conductor into an insulator and then to a superconductor. So how it happens? This is another experiment that came out several months ago from the Columbia University, collaboration with UC Santa Barbara. And again, on twisted bilayer graphene, at a different twist angle. This is at a larger, slightly larger twist angle. Instead of 1.1 degree, this is about 1.3 degree. And in this system, at ambient pressure, as a function of the carrier density, is always metallic. No sign of superconductivity, no sign of insulators. But when a pressure is applied, for example, 1.3 GPa, we see again superconductivity and insulating states. Okay, when we add just a tiny amount.
How is the pressure applied?
I think it's some diamond cell. That's my understanding. Like, yeah, I'm serious. I don't know much about the details. Probably some diamond cell that applying pressure.
Okay.
Yeah.
But in effect, they put a liquid that transmits pressure. They put the sample in a liquid that transmits pressure, and then they put the whole thing in a box which can be squeezed. The box is this diamond cell. It's really 2 pieces of diamond with a big screw on the top that just pushes them closer together.
I got it.
Great, thanks. Right. So again, no, this shows a small variation of the condition is enough to turn a conductor into interesting states. So this is another system that came out about almost 20 years earlier. So this work is as little known as twisted bilayer graphene now is widely known. Okay, so very few people know about this work. So this is a semiconductor system, lead telluride and lead sulfide, or lead telluride and lead selenide. When you grow these materials at the interface, there's an array of dislocations that shows up because of lattice mismatch. And if you look at the period of these, the distance between these dislocations is again on the order of 10 nanometers. Right? So very much like the size of the superlattice unit cell in twisted bilayer graphene. And again, in this system, superconductivity appears at low temperature. So here, actually, superconducting TC is even higher. It's about 6 Kelvin. Right? So these experiments did a lot of study, and they actually concluded that superconductivity in this system has a lot to do with the dislocations. For example, the superconducting transition temperature is correlated with the distance between these dislocations, depends on the superlattice unit cell. Okay, so at the very end of this talk, I'm going to make some connection. Okay, I'll point out the similarities and differences between this system and twisted bilayer graphene. Okay, so obviously, this system is a system of many electrons, and the interactions between electrons are playing a fundamental role in driving these very interesting phenomena. And it's also a hard problem. It involves a hierarchy of energy scales, a hierarchy of length scales. Right? So the fundamental constituent are carbon atoms, electrons in carbon atoms, and the energy scale associated with the atomic orbitals, s and p orbitals in the carbon atom is on the order of, say, 10 electron volt. And when carbon atoms form this two-dimensional sheet, this single layer of graphene, the physics that we usually consider in the graphene is only energy scale of 1 electron volt. Right? Okay, this is the energy scale where direct fermions talk about appears in graphene. And then by the time you come to 2 layers of graphene, which are stacked on top of each other with a twist angle, then the typical energy scale goes to 100 millieV. Okay? And at this very special twist angle of about 1 degree, there's a so-called flat band that appears, which has a bandwidth of about 10 millectron volt. And finally, when you cool the system down to 1 Kelvin, all these things like insulating state and superconductivity appears. Right? So all the way from the fundamental constituent to this emergent phenomena, it spans an energy scale of 5 orders of magnitude. So this is kind of the challenging problem for computations, also for theory, analytical understanding. Right? Involves a big range of scales. So, so briefly, very briefly, the carbon atom has electrons. They arrange themselves in these so-called sigma and pi orbitals when they form a graphene. So the px and py orbitals, they strongly bond with each other. They form these so-called sigma bands that are very far away from the Fermi energy, while the pz orbitals, these are the important building blocks to understand the electronic structure of graphene, they form the conduction and valence bands. Right? And so this is what the band structure of graphene looks like. The energy as a function of momentum in the so-called Brion zone. And the low energy physics, they all occur near the corner of the Brion zone that form this so-called two-dimensional Dirac fermions with zero mass. And this is the Hamiltonian describing the massive Dirac fermion. And this Dirac description is a good description all the way to the scale of electron volt. So here, the Dirac fermion has two components, which are called sigma. We use sigma z, 1 and -1. They really correspond to the two carbon atoms forming the so-called A and B sublattices. So if you look at, for example, the electron wave function on one sublattice, on the B sublattice, for example, is plotted here. You see that there's actually a very rapid variation in the phase of the wave function on the lattice scale. Okay, so this is telling us that although we use a continuum field theory to describe the low energy excitations, one should not forget that there's the actual block wave function has an atomic part that varies on the lattice scale. Also here, tau z, it labels the two values. So there are really two different flavors of Dirac fermions at the k and k prime values, okay, in the system. So when the two layers of graphene are stacked on top of each other, there's interlayer tunneling. So electron can hop from one layer to the other. This is the general form of the tunneling Hamiltonian. This hopping integral is on the order of 0.1 electron volt. And one can rewrite this tunneling Hamiltonian in momentum space. And then we get this form, which is a starting point of our investigation. This was actually a beautiful work by Alan MacDonald back in 2011. So here, what happens is that the twisted bilayer graphene has a very large unit cell. So the reciprocal vector of the superlattice, which we call G, is very small. Right? So when electrons hop from one layer to the other, they can have a momentum transfer, which is the reciprocal vector of the superlattice, and that is equal to the difference of the reciprocal vectors of the two layers, which are called G1 and G2. Okay? So G1 and G2 can both be on the atomic scale, 1 over lattice constant of graphene, but the difference between them can be very small. Okay? So the momentum transfer can be very small. So, so here, let me describe the main feature of this problem in terms of electronic structure. This interlayer tunneling essentially hybridizes Dirac fermions on the two layers. And this is here, this is how the Brion zone of the superlattice is obtained. So these red and blue hexagons are the Brion zone of the two graphene layers. And this black small hexagon is the mini Brion zone of the superlattice. Okay? And again, we see that the reciprocal vector of the superlattice is basically the difference of the two fundamental, the primitive reciprocal vectors of the two layers, B1, B1 tilde, B2 and B2 tilde. Yeah. Okay, so so when the two layers are coupled, there's two types of scattering processes. One is a scattering between Dirac cones of the same value, right? The two adjacent Dirac cones nearby in momentum space, only separated by a small momentum. And in this case, the momentum transfer is very, very small, right? It's very, very small. And in this case, the tunneling matrix element can be approximated as being momentum independent. And this is the most general momentum independent tunneling Hamiltonian. There's amplitudes of going from A sublattice of one layer to A sublattice of the other layer, or from B to B or A to B, B to A, right? So these four parameters are sufficient to describe all the all the coupling of the Dirac fermions of the two layers within the same value. And also, because of the A and B sublattice are equivalent, right? They're both carbon atoms. So there's a sublattice symmetry, and that implies that this parameters UAA is equal to UBB and UAB is equal to UBA. So really, we are talking about just two parameters. On the other hand, if we consider inter-valley tunneling, For example, the direct fermion at value k in layer 1, that tunnel all the way to this point, which is a minus k prime of the other valley. This kind of tunneling process requires a large momentum transfer on the scale of the inverse lattice constant. And this really requires a very high order process, right? Very high order process. And that's suppressed. So essentially what happens is that when you have this superlattice at small twist angles, the tunneling operator is locally, you can think of the two layers are essentially homogeneous. But if you want to transfer electrons from one valley to the opposite valley, that requires large momentum transfer, so there's destructive interference. Okay.
Are you talking about just one particle transfer
or
interaction?
One particle. Yeah, everything here is one particle transfer. So because of this destructive interference, this inter-valley scattering is strongly suppressed at small twist angles. So really, we should treat the two valleys as being independent. Okay. So now again, let's look at basically how the direct fermions of the same valley, they hybridize with each other. There are two important energy scales here. So one is that, shown in this picture, when the two layers are misaligned, the direct points are displaced from each other in momentum space, which is given by delta k. And delta k is proportional to sine theta over 2, depending on the twist angle. And this gives an energy scale, okay, which is the direct velocity times delta k. This tells us basically when the two direct cones intersect with each other, at what energy they meet. On the other hand, there's another energy scale, which is the interlayer coupling, which I call U, right? This U is largely twist angle independent. So now comparing these two energy scales tells us there are two regimes. When the direct point displacement, E theta, is larger than the tunneling term U, that's so-called the perturbative regime. And we can really think of the physics as two direct fermions that hybridize only when they meet each other in energy. But on the other hand, when the interlayer tunneling is larger than the direct energy displacement, this occurs at very small twist angles below 2 degrees, then we really enter the so-called non-perturbative regime. And this is all pointed out in the work by McDonald. And in this non-perturbative regime, really the direct fermions of the two layers strongly hybridize with each other. Okay, and new features arise.
In the previous slide, you really mean to compare E theta and U.
E theta and U, yeah, sorry.
Not
Yeah,
T.
that's E theta and U. Yeah. Thanks. Yeah. Okay, so now I've described to you the sort of the physics from carbon to graphene to twist valley graphene, and let's now move on to twist valley graphene at special angles. Okay. So using this so-called continuum model, where only relying on these two parameters, tunneling between the same lattice or the tunneling between two different sublattices, which we call U and U prime, the band structure of twist valley graphene can be computed. Right? So, although the unit cell is huge, consists of 10,000 atoms, the band structure can all be computed with just these two parameters. It's quite amazing. And in this beautiful work by McDonald, they used one further simplification that they choose U equal U prime. And this really applies to so-called non-distorted structure when the two graphene layers are just perfectly hexagons and they are just rotated relative to each other. Then what basically happens is that the area where the A side coupled to A side and the area where A side couples to B sides are essentially equal. That's why the two types of tunneling of equal strength. And in this case, they computed the band structure for different twist angles, and this is shown here. Okay, and in all cases, you see that there remains direct fermions near charge neutrality point, but the direct velocity is strongly reduced. Okay.
So I thought the cone, Dirac cone, required inversion symmetry to be preserved.
Right. Yeah, in this continuum model, there is,
but not in reality.
Not in reality. Not in reality. Right. We'll come to this point later. Yeah. So the direct fermion is present, and the continuum model is actually a good description as small twist angles. So that's okay. So the direct fermions are present, and the direct velocity is strongly reduced. Right? We see that direct velocity is strongly. This is because of the interlayer hybridization. But then something very strange happens around 1 degree, right? And you see that a nearly flat band appears. Okay. So these authors notice this phenomenon, and they call it the magic twist angle. Somehow the flat band appears at this angle. And this actually inspired later experiments to explore twist ballet graphene around this angle. Now, one thing I want to point out, right, which is I think it's important, is that within this particular parametrization where u equal u prime, this flat band is really connected to higher bands. There's no clear energy gap between the flat band and higher bands. In particular, around this magic angle, the flat band actually touches with the higher bands. The gap really vanishes. Okay? So this should be a cause for concern, okay? Because if we want to sort of write down a model that only describes the flat bands, right, we are implicitly assuming that other bands are far away in energy. We can neglect them, but that's not the case here. Or another way of thinking about it that just to take any time binding model you like, you can artificially plot the band structure in the mini Bron zone by doing band folding. Right? After you do band folding, it will appear that you have a flat band, you have a very narrow band, but we know that we're just fooling ourselves. Right? So only when the lowest bands and higher bands are separated by an energy gap, this physics of narrow bands becomes important. Okay, so one of the things we look at is to look at this energy gap, okay, between the lower bands and higher bands. It was pointed out already a while back that lattice distortions are very important when the twist angle, especially when the twist angle is small. So here's what it looks like if I'm looking at a side view, right? You see the lattice actually become corrugated. So the distance between the two graphene layers varies, right? Varies. And what essentially happens is the following: that when we look at the stacking of the two layers, in some regions in the superlattice, where we have two graphenes that are perfectly aligned, this is called A stacking. And in other regions, the two graphene layers are rotated by 60 degrees. They're called AB stackings. So for a perfect graphene sheets that are just rotated relative to each other, you have equal areas of AA stacking and AB stacking. But on the other hand, it is known that the AB stacking is thermodynamically much more stable than AA stacking. Right? So what this lattice distortion does is to enlarge the regions of AB stacking and shrink the region of AA stacking. So energetically, this is more favorable. And the variation of the distance between the two layers is actually quite substantial. From the A region to AB region, the distance varies by more than 10%. Okay, so this is a very important effect. Okay. So in this work with Cochino, we look at the effect of this lattice distortion on the electronic structure, and because the area of the A region is bigger than the area of the area of the AB region is bigger than the area of the AA region, the tunneling matrix element UAB is kind of bigger than UAA. And a lot of calculation by Cochino, we found that this parameter U prime and U are given here. These are computed exactly using just the fact the distance between the two layers varies by about 10%. So these are the parameters that corresponds to this system. And here you see that if we look at the band structure again, now this flat band is separated from the higher bands by a gap of about 14 millielectron volt. And this compares well with experiments. In experiments, when we have 4 electrons per superlattice cell, you see there's an energy gap, and this energy gap is temperature independent. So this is attributed as single particle gap due to the formation of the superlattice. Okay, so this energy scale is about a few tens of millielectron volt. So essentially, the punchline here is that lattice distortion opens a gap between the flat band and the higher bands, so we can really focus on the flat bands themselves. And also, the flat band, although I call it flat band, it still has a bandwidth of about 8 millielectron volt, around 10 millielectron volt, and there are really 4 bands that are tangled up together, and these 4 comes from the two valleys and coming from the two sublattices, okay, the AB sublattice. Okay, so now we're going to zoom in and look at the physics in this flat band. So the two values are related by time reversal symmetry, and because inter-valley hybridization is negligible, so we can really sort of divide these flat bands into two, two per valley. You know, look at two valleys independently, and because there's no inversion symmetry, it means that although time reversal symmetry relates states of k and minus k, they also relate the two valleys. So within each valley, the energy momentum relation is not k2 minus k symmetric. So these are the main features. And this feature really holds not only at the magic angle, but also it's more general as small twist angles. Okay, so this is a zooming in of the flat band at this 1.1 degree. And here are these bands shown. And what you see is that depending on the carrier density, the Fermi surface is going to change dramatically. So near the charge neutrality point, we have direct pockets, right, at the two corners of the mini Bron zone. As we increase the carrier density, eventually near the complete filling of the narrow bands, that corresponds to 4 electrons per supercell, we will end up with Fermi pockets that are surrounding the gamma point. Right? So there's really a change of the Fermi surface from pockets surrounding K to pockets surrounding the gamma points. And this leads to a kind of Lifshitz transition where the Fermi surface topology changes, and that leads to Van Hoff singularities. Okay. So the physics is going to be very different when we're near charge neutrality or near the complete filling of these narrow bands. Okay, so this type of Lifshitz transition is actually seen from Hall measurement. So this is data from Corradine and Andrea Young's group. And this is at 1.3 degrees, and this is the Hall density. So this is charge neutrality point. And as we increase the carrier density, we see that there's a sign change. Right? So this indicates a changing from Hall to electron carriers. Right? So this is...
This is actually experiment?
It's actual experiments. Wow. Yes, actual experiment. Yeah, so it's pretty... Yeah. Right, so next time I teach undergrad physical solids, I can use this example, right? If you complete a field band, you really change from electron to holes. Yeah, so this happens. And notice that this Lifshitz transition occurs actually very close to half filling. And this so-called 2 electron per supercell is where the metal insulator transition occurs when pressure is applied to this device. Okay, so we really have Lifshitz transition near 2 electron per supercell. Also, when these pockets start to merge at the Lifshitz transition, we expect the so-called Van Hoff singularity, where the dispersion become a saddle, has a saddle-like dispersion. And this kind of Van Hoff singularity, okay, this kind of a Lifshitz transition leads to a peak in the denser states, and that's also seen in experiments. This is from Eva Andrews' group, actually almost 10 years earlier. They were looking at STM tunneling into just graphite. But for reasons I don't know, but the top, for naturally graphite, the top layer is very often detached from the next layer, and it's free to rotate. So in some regions, they find different twist angles. Okay, so this is in this region, for example, the twist angle is about 1.8 degree, and you see there's a Van Hoff singularity, right? In the conduction band, Van Hoff singularity in the valence band.
These are what? 1 over square root singularity?
This is in 2D. In 2D, what is it? I forgot. In 2D.
It's stronger than a log.
In 2D, so the whole singularity in 2D.
Probably 1 over square root.
Probably, yeah. Okay. Right. So, so this Van Hoff singularity, in this 1.8 degree sample, they are about 15 milli-electron volt apart from each other. This gives you an idea of the energy scale for 1.8 degree device. And now another region, this is the tunneling data at 1.1 degree. And now you see this Van Hoff singularities are still there, but they are only 10 milli-electron eV apart. Right? This is again showing that the energy scale goes down as you go to smaller twist angles. Okay, okay, so now I've described basically the electronic structure in crystal valley graphene, as well as the emergence of narrow bands at the magic angle. So let's now move on to the insulating states and superconducting states. And notice that the insulating states and superconductivity has a characteristic temperature about 1 Kelvin, which is still much smaller than the bandwidth of the narrow band. Right? So this encourages us to think about this weak versus strong coupling approach to this problem. Right? So yeah, just to show that how the resistivity looks like in this device, for example, the resistivity is still metallic-like, okay, above maybe 5 or 8 Kelvin, right? It's metallic. And then only at low temperature, for example, the resistivity starts to shoot up, right? This insulating-like behavior, and also sometimes it goes to nothing depending on where the carrier density is. So this really, to me, it means that the fact that the energy scale associated with insulating state and superconductivity are much smaller than the bandwidth is enough to rule out the scenario of the strong modeling insulator. In the scenario where the Hubbard interaction U is much bigger than bandwidth, we would expect insulating behavior already for temperatures on the order of the bandwidth, but this is not the case here, right? So, this encourages to think about maybe a weak coupling approach first. So, this is the work I'm described with Hiroki Isobe and Noah Yuan. So the fact that the metal singularity is very close to half helium, where this metal insulator transition was found at low temperature, it sort of leads us to speculate that there may be some physics associated with these metal singularities and the nesting that are present in this case. So, this is what the Fermi surface look like, okay? At least what we think it looks like. And you see that these are Fermi surfaces coming from 2 different valleys. They are really independent of each other. And you see that there are these Dirac pockets surrounding the Dirac points. And at this Van Hoff singularity, the pockets from 2 corners of the mini world zone start to touch each other. So this is the Van Hoff singularity. Okay? And if we are slightly below that, we have the pockets like this. We have a density slightly above that. We get single pockets surrounding the gamma point. Okay? So, so in all cases, right, there's either diverging or large density states near these regions. We call those hotspots. So there are in total 6 hotspots. They're all related to each other by symmetry. So the model I'm going to present is basically a hotspot model. We're going to consider pockets near these hotspots, and there are all kinds of electron-electron interactions scattering between these hotspots. Okay? And also, if you look at the Fermi surface, you notice there's also nesting. For example, there is a nesting between these 2 hotspots. The Fermi surface are nearly parallel to each other. So there's a sort of a density wave nesting at wave vector Q minus. If we look closely, there's also density wave nesting at wave vector Q prime. And finally, there's a sort of superconducting particle-particle nesting at wave vector Q plus. Okay? So there are different types of nesting stabilities present. So this leads to all kinds of scattering processes, and that's written here. There are in total 9 different scattering processes within this hotspot model. It looks horribly complicated, but after a while, a simple picture started to emerge. So there are really 2 types of interactions. There's density interaction that are present come from the long-range part of the Coulomb interaction, and these density interactions can be coming from the same Dirac fermions of the same valley, or from Dirac fermions of 2 different valleys, which we call intra and inter-valley density interaction. They are written here. Okay, and then there's also the so-called inter-valley exchange interaction that comes from the short part of the short-range interaction. And these are processes where, for example, you scatter electrons from one valley to the other. Okay, so because the carrier density in the system is so low, the short-range interaction is going to be much weaker than the long-range interaction. So therefore, to a good approximation, the inter-valley exchange interaction can be neglected. So this is very much like in series of extonic insulators at low carrier density. The long-range Coulomb interaction is the most dominant. And when the smaller exchange interaction is neglected, there's an emergent conservation law. Right? There is a charge and spin conservation within each valley. Okay. this emergent enlarged symmetry will lead to degeneracies between different states.
Do you estimate the relative contribution, since lattice distortion played a big role in your story to begin with?
Right.
Just good old electron lattice vibration interactions that you're dealing with.
Yeah, you're saying the phonon, electron-phonon interaction.
Yeah.
Right. But those lattice distortions are still long wavelength deformations, so they do not long wavelength.
Large Q.
No. So inter-valley exchange interaction requires large Q. That's why they are small.
You're looking within the, yeah, that's right. You're looking within each little thingy. Okay.
Yeah. Yeah. Okay. Yeah. Okay. So this is the RG equation. So basically, when these different interactions are all present, they may enhance or suppress each other, and that's captured by an RG equations. So again, this equation is complicated, but really there are two types of processes going on. There's a BCS correction that drives the RG flow, and that's just like in any theory of metals. And in that case, when the bare interaction is attractive, they grow under RG, and if they're repulsive, they become much weaker. Right? They die out eventually. But now, because of the nesting, there are new contributions to the RG equation, and that are terms that comes with these parameters D. So D is what we call the nesting vectors. If the Fermi pockets are exactly parallel to each other, then this nesting parameter is 1. It means that the nesting related correction is as big as the BCS correction. But in general, the nesting is not perfect, so we treat these as parameters which are smaller than 1 in general. Okay, so it's because of the presence of this nesting that the repulsive interactions has a chance to grow. Okay, and that is going to play a role. Okay, so without these nestings, the repulsive interaction is all going to become weaker at lower energy. And this type of approach was used, has a long history. It was used for cuprates, and more recently, it was applied to monolayer graphene. And yeah, so we use this type of analysis to study this problem of just valley graphene. And so here's what the RG flow looks like. And in this case, I've chosen all the bare density interaction to be equal. This is reasonable if the interaction is a long-range Coulomb interaction. So we set all the smaller exchange interactions to be 0, just as a starting point. And we see that that some of these inter-valley density interactions, they decay, while one of them grows. Okay, and the one that grows is, and this is very general RG flow diagram. And we tried many different initial parameters, and what emerged is a very simple understanding. So basically, if we look at these hotspots, these are the interactions associated with the inter-valley density interactions. These are scattering associated with inter-valley density interactions, and you see that the G22 are the scattering processes that involve hotspots that are not related by time Rosen symmetry. While all the two other processes, they always involve a pair of electrons at opposite momenta. So for those that involve electrons at opposite momenta, their RG flow their RG flow is driven by both BCS process and by density wave process. And one is make it grow, the other make it shrink. So when you combine them, because of the BCS nesting is always stronger, so that's why they become weaker. Okay, despite the presence of density wave nesting, the BCS correction dominates, and they decay at low energy. While for this process G22, it involves a pair of electrons that are not related by time Rosen symmetry, so they only grow under the nesting condition. There's no BCS correction that contributes to this process. Okay, so this is very general. So, so from the RG flow of the coupling constants, we also computed the susceptibility for various channels. And we see that, for example, here, two types of susceptibilities grow, okay, under RG. One is associated with density wave, either charge or spin density wave, at this nesting wave vector Q2. This G22 process basically involves two adjacent hotspots. and there is a density wave susceptibility growth at this wave vector connecting these hotspots. And another type of susceptibility that grows is the superconducting susceptibility, but now this is has opposite signs at the two hotspots, 2 and 3. So it's superconducting stability in a D wave or P wave channel. Okay. So this is a very general based on RG flow equation in our model. And what it leads to is a phase diagram shown here. Here the color tells us the susceptibility, and the two parameters are basically the nesting conditions, tells us how good the nesting conditions are. And we see that at a very strong nesting condition, right, when the nesting parameters are large, we get density waves, either charge or spin density wave at the wave vector Q minus. And if the nesting is weaker, then we get superconductivity, either D or P wave. And again, these are general results. And one thing I want to notice is that this nesting parameters, is hard to know exactly. But one interesting sort of feature here is that, for example, this D2 minus and D1 minus tell you that the nesting condition associates different wave vectors, ordering of different wave vectors. Even when we start with a case where the nesting condition is more favorable for ordering a wave vector Q prime, because the entire interaction only grows at the wave vector Q minus. But in the end, we find that only density wave states are wave vector Q minus, connecting nearest neighbor, adjacent hotspots. Okay, this is a robust feature. And again, we see that the degeneracy between charge or spin density wave and the degeneracy between D and P wave superconductivity, and that comes from the fact that we have neglected this smaller inter-valley exchange interaction. So under this condition, there's an emergent U2 cross U2 symmetry. Charge and spin are conserved on each valley, and that is sufficient to guarantee an exact degeneracy. So we expect the degeneracy to be lifted when the smaller exchange interaction is included.
Wait, I'm sorry, that degeneracy is an exact statement about the model when the
when the inter-exchange interactions are neglected,
okay,
yeah.
So
And
it's
I
not
think
a consequence of just one loop.
it's not a consequence of just one loop. It's a very exact. It's exact, yeah. And that is not tied to this approach, hotspot approach. Even if we include the full model, the full Fermi surface, as long as the exchange interaction is neglected, there's an exact U2 cross U2 symmetry. Okay, so now let's look at the spectrum, positive spectrum in the dense wave state at wave vector Q minus, and this is plotted here. This wave vector is close to period 4. Okay, so 4 times 4 reconstruction, and we see that it gaps the full Fermi surface. Okay, if the nesting condition is good, that the full Fermi surface is gapped. There's also a single pocket above the gap, and 2 nearly degenerate pockets below the gap with much heavier mass. So this compares well with the quantum oscillation data that's shown here. Basically, near this half filling insulating states, when we move, it has an energy gap, and as we dope slightly away, quantum oscillation appears, and these lambda levels only has a 2-fold degeneracy. So that's consistent with a single pocket that is spin degenerate. Okay. Now, around the same time as our work, there's a work from Ashwin's group, again, also exploring the density wave fluctuations that drive superconductivity. A lot of our conclusions are similar. However, the difference is here that they consider Fermi surface that is more triangle shaped, and in this case, they consider a density wave ordering at a different wave vector, which approximately has a period of 2, the 2 times 2 reconstruction. And in this case, this charge density wave state does not lead to an insulating state. It actually leads to a metal. Okay. And in fact, we also tried ourselves at wave vector Q prime. We never found an insulating state. But a wave vector Q minus with a 4 times 4 reconstruction, we get an insulating state easily. Okay, so so what are the sort of conclusions we can say from this model study? I think at the very minimal, in our picture, the superconducting state and density wave state are really driven by the same interactions, the repulsive Coulomb interaction, and especially the long-range part of Coulomb interaction. And these interactions, they grow at low temperature due to the presence of nesting. So in that sense, both states have the same origin, Now, which phase is realized really depends, in our model at least, depends on the Fermi surface conditions, how good the nesting is. So, right. So this, we think, at least can explain why, for example, in resistivity, we see that there's first a sign towards insulating states, but then at a lower temperature, it goes to nothing. Right? So the susceptibility for both density wave and superconducting instability grows under RG. But here, for example, at the lowest energy scale, one susceptibility diverges first. Right? And which one diverges first depends on details. Okay, so yeah, so here I'm showing the many other works all coming out around the same time, exploring the scenario of density waves for the insulating states. Okay, so now let me move on to the last part of my talk. How much time do I have?
10 minutes.
10? Okay, perfect, yeah. All right, so I've explained sort of this weak coupling approach starting from the Fermi surface instability. And now let's explore another limit where we think about strong coupling. And again here, as a first step, we would like to build a effective model that only describes the flat bands without the need to worry about higher bands, because higher bands are separated by a large energy gap. So, so this is what we're going to do. We're going to look at the band structure. We're going to analyze the symmetries of these lowest flat bands, and we're going to infer the winding orbitals, the center of winding orbitals, and the symmetries of winding orbitals. And also, we're going to compute this winding orbitals explicitly, and that allows us to build a type binding model that fully reproduces the band structure. So one comment I want to make, right, is that one can compute the band structure in various ways, and this continuum model that I've described is a very good approximation. It's a very good starting point. Allows us to compute the band structure, for example, using just 2 parameters. However, when we talk about winding orbitals, they are really defined only for lattice systems, for real materials defined on lattice. So it's impossible to define winding orbitals for a continuum theory. There's no such thing. Okay. So I think that is where a lot of confusion recently in literature come from. Okay, so so now I have to, when I describe the winding orbitals, I have to specify the structure that I'm studying. And as a starting point, let me look at this twist bilayer graphene with so-called D3 structure, where we stack 2 layer graphenes with registered atom. And in this case, the point group has so-called D3 symmetry, 3-4 rotation around the z-axis, 2-4 rotation around the x-axis. And we look at the band symmetries at all high symmetry points in the momentum space. And I don't want to go through the details. And then we try to enumerate all possible combinations of linear centers and linear symmetries so that these kind of band symmetry can be obtained. And there's only one solution, which is that the winding orbitals has to be located at so-called AB and BA regions. They form a honeycomb lattice. And at every side of the honeycomb lattice, there are 2 degenerate winding orbitals. They are of px, py symmetry. They are related to each other by a 3-4 rotation around that site. Okay. So, so in this earlier work, we came to this conclusion that's based entirely on symmetry considerations. And then recently, collaboration with Koshino, who's an expert on these twisted bilayer graphene electronic structures, and we explicitly constructed these winding orbitals. Again, there are 2 valleys that essentially do not couple to each other. So these winding orbitals are constructed for each valley, okay, for each valley. And this is what the winding functions look like. And I'm plotting the winding functions for one layer, for the next layer, for A sublattice, and for the B sublattice. That's why you see 4 different plots. And in all cases, when we look at the angular momentum of these winding orbitals, we find the angular momentum is 1 or minus 1. It has a symmetry of px and py. And notice that, for example, the angular momentum really has 2 parts. There's one part associated with the envelope function, which I call L envelope. But also, remember that as I said earlier, that the block wave function at the direct point on each layer has rapid phase variations within the length of the unit cell. That contributes to so-called angular momentum associated with block wave functions. So only when you add up them, you get the correct photo angular momentum. And the correct angular momentum is plus minus 1, which confirms this px plus ipy symmetry. Also, one thing to notice that although the linear orbitals are centered around the so-called AB and BA regions, the peaks, the weights of the linear orbital are actually away from the center. Right? It has a 3-peak structure, and these peaks are actually centered around the so-called A regions. And that's also consistent with previous calculations.
Are these Wannier functions for the band structure you obtained,
For the
which has the strain so that the central bands are separated from the other ones?
Yes, that's right. For the set of 4 bands that are separate from all other bands.
Right, but that means it was built on the band structure that had this strain effect.
Has a strain. Exactly, absolutely, exactly. Yeah. This is for the case of a 1.5 degree twist angle with this corrugation effect included. Yeah. Right. Okay. So and here, so once we know the Wannier orbitals, we can explicitly compute. We can do Fourier transform to get the Taibani model. Right. So this is a Taibani model, without any fitting. Right. Once we know the Wannier orbital, we compute the Taibani explicitly. So, so this figure represents all the hoppings on this honeycomb lattice, right? So the effective model now is defined with honeycomb lattice, and so so suppose I have electrons starting at the center in this green spots, and it has amplitudes of hopping onto various sites, right? And we see that the hopping amplitude decays rapidly. There are only 3 dominant hopping processes. One is nearest neighbor hopping, it's real, and another is this hopping amplitude T5. Okay, it's also real. Last term is this hopping we call T2. That's purely imaginary. Okay, it's hopping here, right? Also, it's shown here. So this hopping T1, this real hopping T1 and this imaginary hopping T2 is already, we already inferred this in our earlier work, and now from this calculation we know explicitly the amplitude of these hopping processes. Now, with this model, you get because we start from a twist value graphene with D3 symmetry, our Taibani model obviously satisfies the exact D3 symmetry. But what's interesting is that if you look at this model more carefully, you notice that some of the terms, for example, hopping from the origin to this site, second neighbor T, is very, very small. Right? In the lattice with 3-4 rotation, if you write down the most general Taibani model compatible with the D3 symmetry, the second neighbor hopping does not have to be 0. Does not have to be 0. Now, why we get almost 0 hopping? So when symmetry is loud, generally you expect to be present, right? Now, this turned out to has to do with the emergent symmetries in the continuum model, okay? Because the band structure that we use come from the continuum model, right? So. So the continuum model actually has a higher symmetries. It has this value conservation symmetry, the U1. It has a spin SU2 symmetry, it has time reversal symmetry. That has all been considered so far. But also, the continuum model, in addition to the D3 symmetry, has an additional 2-4 rotation symmetry that makes the point group not D3 but D6. Okay, D6. Okay. So it turns out that this D6 symmetry is actually implemented in our Taibani model, but it's implemented in a very clever way that took us a while to figure out. So what happens is that this additional elements in this D6 group, which involves the 2-4 rotation around the z-axis, this operation, this symmetry is present in our Taibani model, but it doesn't simply commute with the U1 symmetry. Instead of being a direct product, it's a semi-direct product, meaning that when the commutator relation between this C2 rotation around the z-axis and the value U1 symmetry is modified. Okay, instead of right here. So if I have 2 operators which commute, then I expect A times B is equal to B times A. But in the semi-direct product, A times B is equal to some phase factor e to the I theta AB times BA. Okay. So so in our model, this additional 2-4 rotation symmetry, it has a twisted commutator relation with the value symmetry. Okay, and in this way, all the symmetries are satisfied. Okay, so finally, once we have this winding orbitals, we can also project the Coulomb interaction or whatever interaction you like onto these flat bands, and we can explicitly construct an extended Hubbard model. And so here are the results. There are two types of interactions. One is the density interaction, and the other is the exchange interaction. The largest interactions are density interactions. And it turns out that the density interactions are not just on site, but it involves neighboring sites. And in particular, when we look at the magnitude of these interactions, on-site interaction, first neighbor, second neighbor, all the way to third neighbor, they roughly fall into this ratio of 3:1:1. So what this tells us is that the dominant density interaction can be written in this way. That's also pointed out, argued for in earlier work by Sento and Ashby. But basically, you take the total charge around every hexagon, and there's energy cost associated with that. And this makes sense because the peaks of the binding functions are located in the AA region. Okay, so basically, the sum over charges around the hexagon essentially counts the actual charge density in the AA spots. Okay. So with this, let me just summarize. All I have to say with the crystal graphene that there's insulating and superconducting states. In our picture, the insulating states is a density wave, can either be a charge or swing density wave, and the superconducting states is either D wave or P wave. The degeneracy between these cases are due to the emergent valley symmetry. It will be lifted by the small interaction, valley exchange interaction. There are various ways. I think on the terminal side, the density wave, charge density wave can be detected by STM tunneling or by some nonlinear IV. Swing density wave can be potentially be detected through the scanning squid, local squid. People already asked the question, electron phone interaction. I think is a very interesting and important problem. Okay, it needs more study. What is the phases of this cluster Hubbard model? These are all open questions.
If you're doing geology, which is what you're doing,
right?
It's in one of the G's.
One of the G's, yeah, the Bayer value. What the Bayer value is? Yes, yeah. Absolutely. Yeah, so Bayer values. One last thing. No, promise to come back to this system of totally different system. Right? These are the experiments I mentioned that lead telluride and lead sulfide heterostructures. Now, actually, we looked at this system a few years back, and in this system, what happens is that as I said, there's an array of dislocations, right, with a distance of about 10 nanometers, and that these materials are, some of these materials are actually topological insulators protected by crystal symmetry. So at the interface, they are Dirac fermions. At least we think they are Dirac fermions. And these Dirac fermions actually respond to strain. So strain acts as a pseudomagnetic field, very much like in graphene, Okay, and at this interface, the dislocation generates a periodic variation of strain. Okay, that corresponds to a periodic variation of the magnetic field, pseudomagnetic fields, and that actually leads to a flat band as well. You see that the Dirac points, the Dirac velocity has been strongly reduced, and flat band appears. So we think that this may explain the presence of interface superconductivity in those systems. Now the difference is that in this system, the Coulomb interaction is strongly screened. Right? This semiconductor has a very small band gap, so the dielectric constant is large. So most likely, superconductivity here comes from electron phonons. And second, at least so far, there's no sign of any insulating states. Okay, it's a superconducting state with TC around 6 or 7 Kelvin, but there's no sign of any insulating states. But I think in general, the general question is that if we have a system of Dirac fermions, that there's various ways we can achieve a flat bands, and interesting things can happen when Dirac fermions are placed in flat bands. Thank you.